In this exercise, we receive a given table with the values for Lx and Ax for certain ages x ranging from 35 to 40. We may assume an interest rate, an annual effective interest rate of 6%. Now do recall that Lx is the expected number of people alive at age x out of an initial group of individuals, in this case 100,000 individuals being alive at age 35. And also recall that capital AX is the EPV, the expected present value, of a whole life insurance in discrete time, working in discrete time periods of 1 year, and the death benefit is constant, is equal to 1, so €1 or $1. Now in the first question here, we're asked to calculate 5E35. So first of all, we need to understand what this symbol is referring to. So this is the EPV of a pure endowment issued to a 35-year-old with a duration of 5 years. So that means, if I look at a timeline, so that means I'm now 35-year-old at time 0. So this is age and this is time. And this pure endowment will pay me a benefit of €1 in case I'm alive, in case the policyholder is alive at time 5 at the age of 40, right? So in order to calculate the EPV of this particular product, we need to discount from time 5 to time 0. So we're going to use V05 or V to the power 5. And we also need to take into account the survival probability. So that is in this case 5P35. So the requested quantity, the requested EPV, can then be calculated as V to the power 5 multiplied with the 5-year survival probability of a 35-year-old. Now, in order to calculate this numerically, this EPV, I'm going to use the given facts in this exercise. So I'm going to use my interest rate of 6%, and I'm going to use my table, my survival table. So in order to calculate this 5-year survival probability, I'm going to look at the number of people alive at age 40 out of the initial group of 100,000 people being alive at age 35. So I'm going to work with L40 divided by L35. And you can do this calculation yourself, and in the end you should end up with 0.73594. That concludes part A in this exercise. If we move on with part B in the exercise, we're asked to calculate the EPV of the product that is referred to by this international actuarial symbol. So if we carefully look at this symbol, we'll see that there is no bar on top of the capital A. So that means we're dealing with a life insurance product in discrete time, in this case, in periods of 1 year. We look at a product issued to a 35-year-old, and the product has a duration of 5 years, right? There is this 1 on top of the 35, so that means that the insurance product pays out in case the 35-year-old policyholder dies before the end of the contract. So that means if he or she dies before reaching age 40. So this is a EPV of a €1 term insurance product issued to a 35-year-old with a term of 5 years, with a duration of 5 years, right? And it's a discrete time product. Okay, so then we know how we can value this using what we learned in the course. And more specifically, we're going to use the connection between the whole life insurance and the EPV of the whole life insurance and the term insurance. So something we did a among others in the class of September 17, was that we can write the EPV of a whole life insurance issued to a 35-year-old as a summation. We can split it in a term insurance issued to the 35-year-old with a duration of 5 years, plus then the EPV of a whole life insurance issued to a 40-year-old. But then we must not forget to actuarially discount this EPV of the whole life insurance issued to a 40-year-old. We need to discount it actuarially from time 5 to time 0. So we need to put this pure endowment and this actuarial discount factor, we need to put that in between. So if you don't see right away where that is coming from, I'm going to write it in full. So using the summation formulas, just to make sure that we understand where this expression is coming from. So if we look at the EPV of the whole life insurance, we look at a sum over k of v to the power k plus 1 times kp 35 times q 35 plus k, right? And now we're going to split this sum running from 0 to plus infinity into two parts. And the first part will go from 0 to 4. So there you've got v to the power k plus 1, kp 35, q 35 plus k, plus then the sum for k running from 5 to plus infinity of v to the power k plus 1, v to the power k plus 1, kp 35, q 35 plus k. And now something that we can recognize in this last sum over here, we can put something in front because all the terms in this sum share the v to the power 5 multiplied with the 5-year survival probability of a 35-year-old. And how can you see this? You can see this because the k here starts from 5 on. So you'll here have in the first term v to the power 6, and then here you have the 5-year survival probability. Then in the next term you'll have v to the power 7, you'll have the 6-year survival probability, and so on and so forth. So if you manipulate this expression, if you look at this, if you look at the first part, you'll recognize your EPV of the 5-year term insurance product issued to a 35-year-old, and then you can put the v to the power 5 times 5p35 in front, and then here you've got the sum for k running from 0 to plus infinity of v to the power k plus 1, and then you'll have kp 40 times q 40 plus k. So in the end, the expression that we retrieve over here looks like this. And that's exactly what I used before, right? So if I need to know what is the EPV of the term insurance, then I know that I can see it as the difference between the EPV of the whole life insurance issued to a 35-year-old and then the pure endowment and the 5 capital E35 multiplied with the EPV of a whole life insurance product issued to a 40-year-old, right? So if we can use this expression, then we see how to calculate what we need to calculate. So what we're going to do then is we're going to use, and I'll continue over here for the term insurance EPV, we're going to use the A35 minus VE35 times A40. And all of that is given in the table, so you can easily do the numerics. And in the end, you should find a value like this, right? Now in part C of the exercise, we are asked to calculate the EPV of a whole life insurance that is issued to a 35-year-old, but with a deferred period of 5 years. So that means we're going to sell this policy to a 35-year-old at time 0, and the insured benefit will be a death benefit of €1 lifelong. but the death benefit is only guaranteed from age 40 on. So if death happens in the first 5 years of this product, there will be no death benefit being paid. So if you look at a timeline of this product, you're going to look at the following settings. So we have a 35-year-old at time 0. So we've got time and we've got age. And we need to take into account the first 5 years as a period of deferment, right? So the death benefit is guaranteed from here on. We've got a death benefit of €1 per year, payable at the end of the year of death. Okay, so if that occurs during these first 5 years, there is no benefit. There is no death benefit payable. And we need to know the value of this product. We need to know the value at time 0, right? So we want to value this product here. So calculate the EPV, calculate the expected present value at time 0. So what do we see? Well, in fact, what we need is this whole life insurance issued to a 40-year-old, right? But we need to value this thing at time 0. So we're going to discount over a period of 5 years, but we're going to discount with an actuarial discount factor. So we're going to use not only the financial discount factor, but we're also going to multiply with the 5-year survival probability. If you want to see how that works, or how I can come up with this expression starting from the summation formulas on, let's do that once again. What we then see is that if you look at this deferred insurance product, if you would write it down with a summation formula, you would start from k equals 5 and go to plus infinity, and you would be working with v to the power k plus 1, kp 35 times q 35 plus k, right? And once again, and this reasoning is similar to what we did in part B of this exercise, if you look at the terms in this sum, they all share v to the power 5 multiplied with the 5-year survival probability of a 35-year-old. So we can put that one in front, and that's what we're gonna do. So we can rewrite this expression as v to the power 5 multiplied with 5p35 times the sum for k running from 0 to plus infinity of v to the power k plus 1 times kp40 times q40 plus k. And that is exactly equal, or there we exactly recognize the EPV of a whole life insurance issued to a 40-year-old. So that's how I know that I should calculate the EPV of the deferred whole life insurance product by actuarially discounting the EPV of the whole life insurance product issued, in this case, to a 40-year-old. And then, of course, you can just get the correct numbers from the table, and eventually you'll get an EPV of 0.138719. In the last part of the exercise, we're going to look at the EPV of a continuous time product. And the way how I recognize that this is the EPV of a continuous time product is because I recognize here a capital A with a bar on top. So this is a continuous product. It's issued to a 35-year-old. It has a duration of 5 years. And I also see that there is no 1, neither on top of the 35, neither on top of the 5-year duration. So that means I'm looking here at the EPV of a €1 endowment insurance. So I've got a combination of a term insurance and a pure endowment. And this product is issued to a 35-year-old. and it works in continuous time. So that's important. And the exercise mentions that we can value this product assuming UDD. And why do we need such an assumption here? Because we are asked to calculate numerically the EPV of this product in continuous time. But the only thing we've given is a table with annual information, let's say, information for discrete values of the hx, right? So we need to make an assumption. And in fact, we covered that in the class. And this is what we learned in section 4.5.1 of our Dickson, Hardy, and Walters book, right? So there we discussed, more specifically in formula 4.25, that I've got the following approximation formula. So I've got, for the whole life insurance issued to X with a death benefit of €1, I've got I divided by delta times the whole life insurance, the EPV of the whole life insurance issued to X in discrete time, right? So I can use that relation, okay? But this one is given for the whole life insurance product. And my question here is about the endowment insurance. So first of all, I'm going to reflect upon what does it mean if I'm dealing with this endowment insurance. Well, the endowment insurance is, and that's the first thing to observe, it's the combination of a term insurance with a duration of 5 years in continuous time and a pure endowment. And the pure endowment has as its EPV this pure endowment factor, and this was v to the power 5 times 5p35, right? So that means if I would picture a timeline for this pure endowment example, if I would make a timeline, what's going to happen then is that I've got a 35-year-old at time 0, so this is age and this is time. I've got a duration of 5 years. And here, between time 0 and time 5, I've got a continuous time term insurance that is active. Okay, so I need to value this part of the product. I need to value this using what I know for a continuous time insurance product. But then there is this pure endowment over here, exactly at time 5, right? So I also need to calculate the EPV of this pure endowment with that benefit of €1, which is payable at time 5 or at age 40, in case my policyholder survives until time 5, until age 40, right? So this is a pure endowment. Now, many students ask me, to value this pure endowment, should I reason in continuous time or should I reason in discrete time? Well, that doesn't matter, right? It's a single event happening at one specific point in time. So there is no need to worry there about the continuous or the discrete time setting. And the only way to calculate the EPV of paying €1 at time 5 in case my policyholder is alive at that time, that's just the v to the power 5 multiplied with the 5-year survival probability, right? Because we're looking here at a single event happening at one specific point in time. So what are we going to do? We're going to use what we learned over here. We're going to use that to calculate this part of my expression. So we're going to do our maths like this. So it's I divided by delta times the present value of a discrete time term insurance plus the v to the power 5 times 5p35, right? So I already calculated this guy in part B of my exercise. So I already calculated this guy in part B of my exercise. I know what the I is, that's 0.06. I should figure out what the delta is, and then here for this pure endowment, this is what I calculated in part A of my exercise, right? So we can put everything together. This is coming from part A of the exercise. This guy is from part B. The I is 0.06, and to get the delta, I will make the following observation. I will observe that 1 plus I is e to the power delta, so that means that the ln of 1 plus I is equal to delta. So that's what I'm going to use here. Putting it all together, I'll find a value of 0.748974. And that concludes my exercise.